Rise and shine, Explorer. Our oxygen levels are steady, and our battery is replenishing nicely. That's cause for a small sigh of relief. Wouldn't you say? But let's not lose sight of the task at hand. We have another glorious day of repairs to conduct. Today, we're going to shift gears and delve into a bit of digital logic. We'll be learning about bits, data types, and why choosing the right one for your variables can make all the difference. Efficient memory usage is essential for our system to function optimally, especially on low memory devices like our Hero board. Moreover, we're going to expand the depths of our coding efforts. We'll work on a piece of code whose intention is to calculate our ship's battery percentage. Not only will this give us a clearer idea of our power situation, but it will also be a practical application of the concepts we're learning. Ready to get your hands dirty with some binary? Of course you are! Let's get to it! Well, aren't you lucky, Explorer? Today you get to enjoy a bit of a hardware holiday. How delightful for you. We're leaving the wires and boards be. They've had quite enough of your expertise for the time being. Before you start daydreaming about a leisurely day off, let me assure you we're not on vacation. There is still much work to be done. While the hardware is blessedly out of harm's way for a day, we're going to fill the void with a thrilling, deep dive into the captivating world of coding. Yes, that's right. More mesmerizing mazes of bits, bytes, variables, and functions are waiting for your full attention. This isn't just about expanding your tiny knowledge base for the sake of it, you know. We're doing this so we can craft more refined, more efficient code. In layman's terms, smoother operations and quicker fixes lead us to a faster escape from this underwater blunder that we're in. So buckle up, Explorer. It's high time you familiarize yourself with the finer points of our Hero board's language. We've got some serious coding to do. Ah, joy! It seems you're thirsty for knowledge, Explorer. We'll hold on to your seat. I'm about to drop some wisdom bombs on you. First, there's this delightful little thing called a bit, the smallest unit of data there is. It's binary, which in this case means it's either 0 or 1. Its simplicity is quite adorable, isn't it? Combine 3 of these and boom, you have 8 unique integer numbers. Mathemagic. Next, let's graduate to the integer. It's a little bit chunkier, with a typical size of 16 bits. This gives you a marvelous range of about plus or minus 32,768. Not too shabby, wouldn't you agree? When it comes to integers, we're not bound by one path to stroll down. We've got 2, signed and unsigned. The signed integers take more of a straightforward path and have a bit that acts like a flag for whether the number is positive or negative. Unsigned integers, on the other hand, don't bother with this. As free spirits, they take the scenic route, living their life positively all the way, hence the bigger range of numbers. Now, take our photoresistor. It's a modest creature, outputting a value between 0 and 1023. It's just 10 bits worth of data because 2 to the power of 10 equals 1024. So, an integer is more than adequate to store it. But don't get too comfortable. Our battery capacity variable is set at a lofty 50,000, which outclasses the standard short integer maximum of 32,768. Thus, it needs the VIP treatment, which defines it as an unsigned integer. Next up, meet float. This one likes to live a bit on the edge, handling decimal numbers with precision. Imagine 123.4567. It has a precision of 7. Not bad, huh? Then there's double. It's a float that hit the gym and got buff. It's 64 bits of power capable of holding values up to a mind-boggling 10 to the power of 308. Veering off from variables, let's shine some light on void. It's what we use when we're defining functions that don't give anything back. We'll dive deeper into creating our own functions soon enough. So there you have it, a crash course in basic digital logic. Its overwhelming nature is similar to drinking from a fire hose. I know, but fret not. We'll be practicing these concepts soon enough. Shall we push on, then? Today's mission involves writing additional logic in order to print the battery percentage to our handy serial monitor that we discussed yesterday. Of course, we don't want to spend time rewriting the print statements all over the place in our code. Instead, we can create a new function. We can start with the word void. This is what the function will be returning. As you may have guessed, void means that it will return nothing. This also means that we don't need a return statement, since the compiler deems it unnecessary. I recommend you name it something relative, such as print battery percentage. The parentheses can be empty since we have no parameters we need to pass into the function. Finally, everything inside the brackets is what will execute when you call the function. When the second closing bracket is reached, it will return to where it was called from in the code. If my assumption is correct, it is likely setup or loop. In the end, your newly created function might look something like this. For the line by line, let's jump to the information cached on your computer. I've also added this to your mission resources for future reference. I'll be waiting patiently for your return.
Hello and welcome back to day 7 of the code explanations. Today we're going to be using the circuit from day 7 to use the value read from the photoresistor to simulate charging our lander's battery. Our battery is currently drained, and we can assume just for simulation purposes that the current charge level is going to be 0, and we will stop charging once the battery is full. So first we explicitly included Arduino.h. As always, if we just happen to delete that entirely, it wouldn't really matter because the Arduino IDE, the one we're programming in right now, will automatically add that in again for us later. I'm also going to close out of a couple of comment blocks that aren't really that big of a deal to go through so that it will look a little bit less daunting. So, new concepts that we're introducing today are going to be, we know of the function setup, that's a default inside of the Arduino IDE, and we know of the function loop, which is a default part of any Arduino program or sketch. However, what do you do if you want to add in your own function? And that's what we're going to be learning today. We're going to be creating a new function, and this function is going to help us with our task of printing the battery charge level, and we're going to call it, quite literally, void, which is what's needed to create a function that returns, well, nothing or void, print battery charge level. And then the syntax for this is, if I actually go like this and close this out, you can see the syntax without anything inside. Void print battery charge level, we have open parenthesis and close parenthesis. Since there's no parameters we're going to be passing in this function, we can just leave it empty. And then we have an open bracket and a close bracket. Anything in between this open bracket and this closed bracket will be what happens when you call this function. This will be the code that it executes when you call it. So if I, at any point during setup and loop, or anywhere else in the code, want to call this line of code, and I do here on line 65, it's going to jump to this function and execute the code located right here. So let's start off by just going through the general flow of the code. First, obviously, we are talking about the analog photoresistor pin. That's going to be on analog pin A0, and we're just defining that above as a constant byte. Same thing as if you used a pound define. Both methods are valid, and you can do either one. Here, down below, we have a constant unsigned integer, and we're going to be calling it battery percentage is going to be equal to, or battery capacity is equal to 50,000. And this is going to be the maximum battery capacity for simulation purposes. We just chose a random large number, in this case 50,000, for simulation reasons alone. Now, if you jump down to setup, we're going to set the photoresistor pin as an input so that we can read off of it and read the value on it. And then we're going to start serial up again at 96,000 baud rate, which means if you do go to the serial monitor, please make sure that you have selected the correct baud rate at 9600 because that's what we set it to here. If you select something else, it will be gibberish. Now, if we jump down to the next part here, we have unsigned int battery level is going to be equal to 0. For simulation purposes, we're going to pretend that our battery is completely dead, which, to be honest with you, it almost is. Next, we're going to jump down to the after setup. It will always go straight to loop. Now, here's where we do something really interesting in loop. We have the following information that we're just going to be spitting out to the serial monitor. If the battery level is less than the battery percentage, meaning this is we're only going to be printing things out if it needs to be charged still, meaning it's not fully charged, then we're going to execute the following code. Battery level and then this is a new concept. Plus equals analog read of the photoresistor pin. So if the light is really, really bright on the photoresistor, then what it should do is it will add a higher number to it. So we can read anywhere from, maybe if it's really dark, it's only going to add 20. But if it's really, really bright, it might add 140, for example. Or, or I guess maybe like it could add up to 200 or 300 as you get brighter and brighter. So what happens is this function here simply adds whatever is in analog read, whatever this is, every time this hits this code, to what the current battery level is. Another way to write this exact same piece of code is, and then this is so line 50 and line 51 will be functionally equivalent. And so this is just a shorthand way of saying battery level equals battery underscore level plus analog read photoresistor pin. So why is this important? That's because in the Arduino language, which is based off of C, there are going to be a lot of shortcuts that you might notice or recognize here and there. This is exactly one of those shortcuts. Battery level equals battery level plus analog read photoresistor pin is the exact same as battery level plus equals analog read photoresistor pin. It's simply just a shorthand so you don't have to type it twice. It also looks a little bit cleaner, at least in my opinion. Another shorthand that you'll see from time to time is, let's just say you want to say battery level equals battery level plus 1. Well, there's an easier way to do that, and that is you can just do plus plus. And that simply just adds 1 to there. But we don't need to do that. That's just another example of a shorthand that also exists, that maybe one you might be more familiar with. Battery level equals analog read, or plus equals analog read photoresistor pin. So we're just going to add whatever this is to battery level. Then, if the battery level is greater than the battery capacity, meaning this would make the charge over 100%. So let's just say that the battery level was 49,980 and it added 30 to it. So now it would be 50,010 once it gets to this line out, because maybe in this one it made it too higher than 50,000. Then we're just going to reset it back down to the maximum capacity, making the battery level back at 50,000 since we can't obviously charge it more than the maximum amount. And then the next time we go through the loop, you'll notice that it will probably hit this code here. And since it's going to be fully charged, we'll just be ignoring all of this extra additional stuff inside of here. Next, we're going to call the next function that we created down below, print battery charge level. We're calling this function inside of loop. We're calling a function inside of a function. And what this will do is it will jump here and then immediately execute the following code. So whenever we call this function, it will jump to here and it will say, if it is not fully charged, then we will print the battery level and display it as a percentage to the serial monitor. If it otherwise, meaning it is fully charged, we're going to just display that it's fully charged. And then finally, once this is done executing, it will jump back to the very end of the line here, at the end of where you called the function, and continue on going forward. In this case, it'll go down a line, and it'll delay by 1/10 of a second, and then hop back to the beginning of loop and go through the exact same sequence once again. And so with that, that will be the end of day 7 code explanation. I'll see you again tomorrow.
Welcome to the Day 7 wiring example video. As we mentioned on Day 6, today nothing has changed circuit-wise since Day 6. So we really don't have any new circuit or hardware explanations to go over, although you can review the Day 6 video if you'd like a refresher. Instead, we'll be focusing today mainly on how our circuit interacts with the logic that's programmed into our new Day 7 software sketch. All of the new functionality will be observed this time by looking at the output on the serial monitor console. So without further ado, let's just go ahead and run our software sketch and see what it does. Once it's loaded, we'll see that the serial monitor will give us a running status of the state of charge of our simulated battery system. And so we see a slowly rising number. If we place the photoresistor in the dark with our black cloth, we see that the charging rate basically slows down to 0. And so this is telling us that we're not charging at all. On the other hand, if I remove the cloth, the charging rate picks up again. And if I increase the light intensity even more by shining a flashlight, the rate jumps rather dramatically. So we can see that by altering the illumination on the photoresistor, we see changes in the rate of charging in our circuit. And so if we let this continue, we'll speed it up a little bit by shining a flashlight on it, eventually the charge level will reach 100%. And that should be happening about now. There we go. So the sketch detects this condition and it stops the charge level from rising any higher than 100%. So you'll want to experiment with this on your own while studying the logic that's built in to our sketch for day 7. Good luck with this new bit of coding, and we will see you with more challenges and new things to learn ahead on day 8.
Well, 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 you've made it through the day, Explorer. Our little adventure with bits, integers, floats, and doubles didn't scare you off, did it? Not bad for a human, I must say. Now that we have our power situation under control and can monitor our battery percentage, you must be feeling rather accomplished. Before you get lost in celebration, let me remind you that we've barely scratched the surface of what's broken on this ship. Tomorrow, we're going to brighten up this dreary spacecraft by adding a bit of color. Yeah, you heard me right. We're going to introduce an RGB LED, which can emit all the colors of the rainbow. We'll use this flashy little gizmo for various status indicators, like painting a glowing green if our battery is all charged up, or a glaring red if we're running on fumes. So, get some rest, Explorer. Tomorrow, we paint with light.